This circuit offers a study of two topics: the resistor-capacitor timing effect on frequency, and also a demonstration of the op-amp property of high open-loop gain that leads to saturation and instability. It intends to give the student a direct sensory experience, that is, audio and visual, to reinforce the learning about RC time control and frequency. Observe the three voltages in this simulation. Red is the output voltage V out at node C. Yellow is the non-inverting terminal, which is node B, connected to the output via a potentiometer. And green the inverting terminal, node A, connected to V out via a feedback resistor. At the start, the V out tries to pull node A voltage up with a large feedback current charging the capacitor. When VA gets to be equal to VB, however, because of the high op-amp open loop gain, it takes only a little overshoot or noise to make VA exceeds VB a little, causing the output to flip negative at the saturated voltage. VB follows and also flips, and VA has to chase VB again the other way. The cycle of VA chasing VB, flipping back and forth continues indefinitely, and the circuit becomes an oscillator. How fast each cycle takes depends on the rate of charging and reverse charging of the capacitor, that is, the RC time constant. The frequency can also be changed by tuning the potentiometer, which varies the set ratio of the non-inverting voltage relative to the output voltage. The lower the ratio, the faster VA, that is, the voltage of the inverting terminal, can catch up with VB, hence it results in higher oscillation frequency. With a potentiometer for the feedback, one can control both the amplitude of VA and the frequency. However, you have only one potentiometer, and the circuit needs not be more complex for this particular task. This circuit is built for photographic clarity. The R and C combo for sound is placed far away from the op-amp, leaving room for the RC combo for LEDs, and also room for the wires that lead to two large rows of LEDs, which are used to test the circuit numerical simulation. If your breadboard real estate is not an issue, it is recommended to build a circuit with generous space between the components for the ease of troubleshooting as well as for presentation. It takes time for these calculations, from tens of seconds to minutes. These are calculated LED current and voltage as functions of time. This shows the voltages of the 3 op-amp terminals: output node C, red, inverting input node A, green, and non-inverting input node B, yellow. Notice the frequency with the LEDs is lower than that without. These are default values. They should be changed to the actual values on the circuit. For each change, the circuit is recalculated. Note the difference frequency, different LED voltages and currents, compared with the previous results. These types of behaviors are shown in a demonstration video, in which a photodetector was used to measure the LED outputs. Select the correct LEDs. The calculation uses somewhat old LED calibration, but it can still give some reasonable approximation, and generally qualitatively valid LED behaviors. Notice again a different frequency. Quite different LED currents and voltages. These were actually observed and shown in another video. Select a few positions of the potentiometer, measure the frequencies and compare with this calculation results. This frequency is nearly 3 times the previous, due to the change of the potentiometer knob. A demonstration used a low capacitance, 10 microfarad, to observe higher frequency, for which, the eye cannot tell, and it was measured with a photodetector.